Here, okay. Anyone know what day we are? Are we, I think lecture 14, is that possible? Okay, so math. What the hell is this crap? This marker doesn't work. I had a blue one. What happened to my blue one? I did not throw it in the trash can. I did it today. I went before class and got it from a different classroom. Math 140, lecture 14, we believe. And this is on chapter 16. Confidence intervals. Specifically, the basics. So confidence intervals is roughly 1/2 of the rest of the semester. So chapter 16 is the start of confidence intervals. And the idea of a confidence interval example is that we are interested in knowing a parameter. In this chapter in particular, P will be unknown. Yes. Chapter 16. I had a blue, but I don't know what happened to it. Huh? I brought it today. Where? Oh, my shoe. There it is. Under my shoe. Okay, so P will be unknown. What is P referring to again from last time? Population what? Proportion. So remember, we're splitting this class up into two basic situations. Either we're looking for a mean or we're looking for a proportion. Chapter 16 is when we're looking for a proportion. So P will be unknown. So what do? We take a sample. And we want to use that sample to kind of get a bead on P. So let's say, for example, we're looking for the proportion of Americans who smoke at least once before they're 20. The proportion of Americans who smoke at least once before they're 20. So what do? I don't know this proportion. I'll never know this proportion. People might lie, but let's assume nobody lies in this survey. It's an anonymous survey. So what do? I take a sample. So take a sample. N is equal to the sample size. And X is equal to the number of successes in my sample. In this particular situation, what is a success? Getting a person who says, yes, I smoked. That's a success. So what do we get? What do we calculate? We calculate P hat. What is P hat equal to? It's equal to X over N. That's mathematical. The number of successes divided by the number of trials. But what do we call P hat? What's another name for P hat? No. You can't even read correctly. That's sad. What is P hat? The sample proportion. Well, yesterday was P day. No. It's not pronounced pi, it's pronounced P. No. I mean, I did have pie yesterday, it's true. Both pizza and apple, just so you know. However, the real pronunciation, if you ask anyone who actually speaks Greek, is much closer to P than it is to pi. So we should all celebrate P Day by going to the bathroom multiple times. I know I did. But pi is not the correct pronunciation. So p hat is the sample proportion, whereas p is the what? The population proportion. We will never know the population proportion. The best we can do is get the sample proportion. Now, the sample proportion is our best guess estimate for the population proportion, right? If our sample proportion is 92%, then we're probably going to say that the true population proportion is somewhere around 92%, if we believe our sample was good, correct? But the somewhere around, that's the key of this chapter. Because what we're going to do is not just get one value, but get an interval of values centered at our sample proportion. And we're going to call that a confidence interval, because we are somewhat confident that the true value will be somewhere in there. So the confidence interval is this interval that we create where we have some confidence that we've caught the true value. Now, it is important that the sample size comes from a what? An SRS. Okay, so we have to assume as part of the derivation, even though we're not going to derive the formula, we're just going to give it. What we have to do is we have to assume that we are dealing with a SRS. And for technical reasons, like we had last chapter, we require that n p hat and n times 1 minus p hat are both what? Anyone recall the technical condition we had last chapter as well? N p hat and n times 1 minus p hat must both be greater than or equal to 10. Now, what is n p hat, by the way? What's another word or a few words for n p hat? Mathematically, n p hat is what? Everything you need is on the board. What is n p hat? Sorry? No. Do the math, yes?
The sample portion from the SRS.
No.
Sample size times sample proportion.
Yes, so what does that give us?
Great question.
Well, that's on the board. You don't need to look at any words, it's all the math. What is n times p hat?
All the possible.
Look at the math. The math. What is n times p hat? X. N times p hat is just x. That is the number of successes. We must have at least 10 successes. What is n times 1 minus p hat? What? What is n times 1 minus p hat?
1 minus
X is how many successes? 1 minus X is negative. What? Huh?
1 minus x.
1 minus X is negative.
1 over n minus x.
Ah. What is 1 minus, if p hat is the probability or the proportion of successes, what is 1 minus p hat? What is 1 minus p hat? If p hat is the proportion of successes, huh? What's the number of failures? Wait. What's the number of failures? That. Tell me that. What is that? No, 1 minus p hat is not the number of failures.
And it's a percent of failure.
What?
Percent
Of what?
of failure.
So what is n times 1 minus p hat?
It's a number of failures.
That's the number of failures. That's why I asked. N p hat, this quantity, number of successes. And 1 minus p hat, this quantity, number of failures. In order to use the formula that we're going to derive in a few, not derive, but at least I'm going to give you in a few minutes, the number of successes and the number of failures must both be greater than or equal to 10. What if they're not both greater than or equal to 10? What do we do? Answer, not this. Because in order to use what we do here, this condition must be satisfied. At the end of this chapter, we will do a different formula for the case where this condition is not satisfied. There'll be lesser conditions that have to be satisfied. But if these are not satisfied, don't do this. What we're about, this is all facts. We haven't done anything yet. But to come up with the confidence interval formula that we're going to come up with, we need this. Yes?
Where does time come from?
10 is an arbitrary number decided by experts in the field of statistics to ensure that what we come up with is reasonably accurate. So it's a number that was arbitrarily chosen, much like 1.5 for the IQR was chosen because it gives us reasonable outcomes. 10 was chosen because it gives us reasonable outcomes. Yes?
So if it's not greater than 10, it's a bad sample.
It means the formula that we're going to use cannot be used. The formula we're going to write down in a minute, do not use it if these conditions are not satisfied. It will not give you accurate results.
Go to the different formula.
Yes. Yes.
So we're not plugging in individual values, we're plugging in formulas.
Say what? What does that mean?
Never mind, I guess we should just do.
Just do it. Okay, so if these conditions are satisfied, then this is the confidence interval. The confidence interval is p hat. That's the center of our confidence interval. It's the best guess estimate, p hat, plus or minus. That means the quantity that goes here, that we're going to put here, p hat minus that number will be the left edge of the confidence interval. P hat plus that number will be the right edge of the confidence interval. So what we do here is we're technically calculating the left and right edge of our confidence interval. P hat plus or minus what? The square root, sorry, before the square root, I left out one thing. Z star, and I will explain what that means, times the square root of p hat 1 minus p hat over n, all inside the square root. Oh. P hat 1 minus p hat over n, all inside the square root. And the question is, what is Z star? So first, Z star is not a number. It's not one number, because if it was just one number, I just write down what that number is and I won't have to write Z star. So Z star depends on one thing and one thing only. How much confidence do you want to have that you caught it? Because if I want to have 95% confidence that I caught it versus 90% confidence or 80% confidence or 70% confidence and so on, that's going to change the width of my confidence interval. Let's think about it in terms of fishing. Anyone here ever go fishing?
Yeah.
Interesting. Okay. People still do that. Fine. So imagine you don't have a fishing pole. You just have some kind of net. I'm not sure if this even works, but it's just an analogy that I came up with. Or maybe you were catching butterflies. Butterflies, that makes more sense because they're flying. You can have a little net and you try to catch them. So if you're trying to catch butterflies and you want to be more confident of catching one, should you use a smaller net or a larger net? larger net. So greater confidence. Greater confidence does what do you think to my interval? Does it make the interval bigger or does it make the interval smaller? Bigger. If you want to have more confidence that you caught whatever you're trying to catch, in our case P, the more confidence you have, the wider the confidence interval is going to be. If I want to be 100% confident that I caught it, how wide should I make my interval?
100.
How about 1,000,000? How about 1,000,000,000? How about infinite? If I want to be 100% confident, I promise you, if you go from negative infinity to infinity, you caught it. I promise you that. If I want to be 0% confident that I caught it, make it a single number. Have no width to my confidence interval. Right? Or essentially 0%, unless I'm really, really lucky. The more confidence you want to have, the wider the confidence interval. Yes?
We would know that, like, based off the question if I asked us this, like, oh, find, like, your confidence, whatever is like 70 or whatever.
I'm not understanding your question.
Like, for us to know what to put for Z, the question was.
Well, I haven't told you how to calculate it yet. I have not given you that information. I have not told you how to calculate Z. No, I just told you that the more confidence you have, the wider it's going to be. But I have not told you how to calculate Z star yet. But I tell you, if I give you a 90% confidence problem, and then I give you a 95% confidence problem, and you calculate Z star for both of them, what I'm telling you is 95% confidence, your Z star is going to be bigger. Because a bigger number for Z star means you're adding and subtracting a larger number. If you add or subtract a larger number, it's going to make a wider interval. So greater confidence, wider confidence interval, bigger Z star. More confidence is going to have a bigger Z star value. Yes, was there a hand up somewhere? Yes.
So they correlate.
They correlate. Positively correlated, to be more specific. A larger amount of confidence creates a wider confidence interval, which is arrived at via a bigger Z star value. So what can, yes?
The way I'm thinking about it is,
How
How are you?
I'm great. How are you?
Good, thank
Good
you.
for you. You're welcome. And there was a 6-point curve, so it's actually 6 points higher.
Oh, okay.
Okay?
Yeah.
All right, that's it done. And someone else came in late as well. I want to make sure that you are marked present or tardy at least. Nobody wants to reveal themselves. Okay, then you're absent. Now, what was your question?
so with the greater confidence, wouldn't it be, the way I'm thinking is smaller is better because you're more precise?
I understand, but if you want to be more confident that you caught it, you make it bigger.
Oh, okay.
The more confidence that you want to have, the larger your interval is going to be. So if I do want to make my interval smaller, because let's think about it. If you make your interval really wide, you might have a lot of confidence that you caught it. But if the interval is so wide that you can't really narrow down the value, then what's the point of having that confidence? Right? I'm 100% confident. I'm going to go from negative infinity to infinity. Great, you caught it. What is it? It could be anywhere. You have the confidence, but you don't have a value. But if you go low confidence and you make it really, really tight, yeah, it's in here, but I'm only 10% sure. Well, if you have really low confidence, then that's not useful either. What you really want to have is high confidence, but a small confidence interval. Well, high confidence makes a bigger confidence interval. So what's the only thing I can do to have high confidence, but at the same time, make my interval smaller? Huh? So there's an average confidence, 95% usually what's taken. 95%, those are the traditional values. But even with that, I can still make it smaller, even at 95%, without touching the confidence. What can I do to make my interval smaller? There's only one thing else I have control over besides setting the confidence level. And that is what?
Is it the Z star?
No, Z star comes from the confidence. I will tell you in a minute how to calculate that. But Z star, whatever your confidence is, that's your Z star. What can I do? Huh?
Like
P hat is the proportion of successes. I mean, that's what I get out of my sample. I can't control that.
make your sample size smaller or wider.
Make my sample size wider.
So smaller. Like, you know.
So you want to ask fewer people or fewer individuals.
It's not weird. Yeah.
Okay, so you're saying the fewer people you have should do what to the confidence interval?
Lower.
Make it smaller?
Yeah.
Yeah.
Does that jive with the math that's currently on the board? That a smaller sample size would make a smaller confidence interval, I mean, a bigger confidence interval or smaller. It does, huh? You're all nodding your head, or some of you are nodding your head.
No.
No. So n is in the denominator. If you make n bigger, if you make a bigger sample size, what does that do to this entire fraction? Make it smaller, which when you multiply by z star is again, making it smaller. So if you want to have a smaller confidence interval, increase the sample size. Increase n makes a smaller confidence interval. So the true balance is you first decide how much confidence you're comfortable with. If I say 50% confidence and you catch it, but you're only 50% sure that you caught it, you might not be really happy with that. So what are the traditional values for confidence? 90%, 95%, 99%. If I tell you that there's a 99% chance that you caught it, would you feel confident that you have it? Yes. So if I make my confidence level 99%, but then I find that my interval is really, really big and therefore useless as a predictive measure, as a predictive action, then I will have to increase my sample size to make it smaller. Does that make sense? I have no control over p hat and 1 minus p hat. Those come from my sample. That's the proportion of successes and failures. I mean, that's whatever I get. I have control over z star and I have control over n. So let's focus for a second on z star. How do I get z star? It's actually quite easy to get z star. In fact, we already know how to get z star. And I'm going to give you a technique that applies for any confidence level, not just 90%, 95, 99. Those are the three, by the way, that a lot of people memorize. They memorize, oh, 90% confidence? Oh, I know z star, it's this. 95% confidence? Oh, z star is that. I even have them memorized. But if I give you on a test 92.6%, well, you got to know how to solve that. Yes?
Why don't we just do 100% confidence?
100%?
99% all the time. Why does it like fluctuate from 92 to 95?
Because the higher the confidence, the wider your interval. And if you want to make your interval smaller, you have to increase the sample size. But sometimes the sample sizes get so big that it's not feasible. So you got to do a balance. You got to say, okay, I have to lose a little bit of confidence for the sake of actually being able to do the sample. So let's do 90% first. Suppose I want 90% confidence. Here is how I want you to think about it, because this approach will work for any level of confidence. I want you to draw a normal curve. And this will be the standard normal curve. So what number is directly in the center? What number is directly in the center for the standard normal? 0. What number? Me. Okay, well, I appreciate that you feel like I know what you meant. Number 1. That's what you meant, but no, it's 0. Oh, it was you. Okay, so 0 is directly in the center. If I want 90% confidence, I want you to imagine cutting off 90% of the data. If I want 90% confidence, I want you to imagine cutting off 90% of the data. What is this number right here? What number is the positive value? Negative on the left, positive on the right. What number is the positive value that cuts off 90% in the center?
1 and 2 standard deviation.
Great, what's the exact number? Or at least the 3 decimals, what's the exact number? This is not something you do in your head. You either go to a table or you go to a calculator. But we should know how to do this by now. We did this earlier in the semester. So what is the value that gives me 90% in the center? If your calculator can do center, then you put in 90%. If your calculator can only do left, what number do you put in for the area? If your calculator can only do 95%, sorry, shit. Hey, you're so smart. So what do I get? Anyone do it? Huh?
1.28.
I don't believe so.
1.6.
1.3
6.
decimals?
4, 5.
1.645. Z star is equal to 1.645. Now, if you got 1.28, I'm curious how you got that. So what did you do to get 1.28? Huh? Oh, inverse. Oh, embarrassing. What a rookie mistake. No. 1.645, you understand how you get it? 90%. Inverse norm, 0.9 in the center. Your calculator can do center, right?
Yeah.
So inverse norm, because we have the area and we want the Z value. 0.9 is the area. Put in the center and a 0, 1 distribution. Yes?
Yeah, I did it. It says 1.28.
Yeah.
What was your area?
0.9.
Center, left or right?
You can't do center.
You can't do center on yours. You didn't do center. Okay, there's literally the word center on the TI-84s. If you don't have the word center, then your calculator can't do center. Your calculator can only do left. So I ask again, what's the area left of this point? No, it should be immediate. 90% in the middle. How much is left of this point? 95%, just 5% over here. 5% here, 5% here, 90 in the middle. So to the left of this point is 95%. So if you don't have on your calculator the ability to do center and you could only do left, you got to put in an area of 0.95. And then it automatically does left and it will give you 1.645. So anytime in this course, you got it now? So anytime in this course, we ever have 90% confidence, you know Z star. What is it? 1.645. What if I want to go 95% confidence? So 90% confidence, I got 1.645. What if I want to go to 95% confidence? Now, if you have center, you can go directly to 0.95, but if you don't have center, what's your area going to be? Huh? No, it's not going to be 100. 0.975. If there's 95% in the middle, that gives you 2.5% on the left. For a total of 97.5%, 0.975. What do we get? 1.96. And 99%, the third of the big trifecta. If you do 99%, again, in the middle, 0.99, but if you don't have in the center and you got to go left, how much is to the left if there's 0.99 in the middle? 0.995, what do you get?
2.576.
What do you get?
2.576.
Is that what it is?
Yeah.
2.576. These are the big three.
Oh, why is the 95 not rounded to the third?
I don't know, that's because books don't do that.
Can we round the first?
Yeah, when I do problems on my calculator, I keep all decimals. So I might round and write down 2 or 3 here. But if I actually do math with them, I keep all the decimals till the end of the problem. Yes,
And so for 95%, I should get 1.96.
well, if there's 95% in the middle, how much is to the left of this point?
Is it 100?
No, how can it be 100? There's still some to the right.
Right?
If the middle is 95%, 2.5. So how much is to the left of this point?
97.5.
Yeah, that's exactly it.
99.5.
Yeah, exactly it. That's exactly it. So any other value I give you, that's not one of these 3. You have 2 choices, your calculator or a table. But if you have a calculator, you got to be very careful. You got to make sure your calculator can do center. Because if it cannot do center, if it can only do left, you got to do a little math to get the right answer. Does that make sense? Okay, so this gives you Z star and allows you to actually compute a confidence interval. Yes?
Wait, so the confidence interval Z star is basically everything in the middle of it?
No, Z star is this number. This number is Z star.
Oh, okay.
Okay, these are my Z stars. So when I go to my formula, that's the number that I use where Z star.
So like,
Okay. So every confidence interval, every confidence interval will be an interval. So it's going to have an LB and a UB. What's my LB? What's my UB? What do those stand for? Lower something and upper something is correct. What's the B? The lower bound and the upper bounds. What's at the center of my confidence interval? What's the exact center? P hat. P hat is the exact center. Because remember, it's P hat plus or minus something. What is this distance here from the center to the upper bound?
1.64.
No. 1.645 is Z star.
178.
No. Go to your formula. What is the distance between the center and the upper bounds? Yes? Sorry? X is the number of successes. But no, don't apologize. It's a good answer. It's got to be wrong. Peter's wrong like almost every single time, but he doesn't stop asking. Right? So the distance from the center to the upper bounds is what you are adding to P hat to get the right side of the confidence interval. Well, go to your formula. What do you add to P hat to get the right side? You wrote it down earlier if you're taking notes. Huh?
The square root of P hat.
Nope. A little closer. Z star square root P hat 1 minus P hat over N. It is the entire thing that you are adding to P hat. Not just the square root, not just the Z star. The entire thing that you are adding.
What is the star set?
For some reason they use stars. I don't know. If you don't write the star, but you understand what it is, that's fine too. It doesn't stand for anything. It just, for some reason, books use Z star. Huh?
What is it?
What is what? Z star is a number. 1.645, 1.96, these are the numbers. These are Z stars, depending on the confidence, yeah?
So it's the plus or minus, right?
It's the plus or minus part. Also called the margin of error. The thing that you add or subtract from P hat to get the upper bound or the lower bound is called the margin of error. What's the distance from the center to the lower bound?
Minus.
Just the distance. Don't worry about negative. What's the distance?
Oh, the same thing.
Same thing. Same thing. You add or subtract the same thing to go left or to go right. The center is P hat plus or minus the margin of error. That's how much you go right. That's how much you go left. That gives you your entire confidence interval. So let's do an example. Okay, let's do an example.
Was the last chapter, was it math, like with your math involved?
Last chapter, I think we had a little math last chapter. Okay, and by the way, just so you know, those of you who have a calculator, which hopefully is all of you, if you hit stat, and then you go right to test, or right to the test, and you scroll down past the tests. After the tests, what do you see? You have the what? You have the intervals. These are your confidence intervals. In particular, today, we're doing the proportion. Is there an, I forgot, is there an interval for proportions? What's it called? So this is a one proportion interval, a one proportion Z interval. So stat tests down all the way to one proportion Z interval. What does your calculator ask you to input to compute a one proportion Z interval? X, which is the number of successes, N, which is the sample size, number of trials, and C level, which is your confidence level. Doesn't ask for Z star. It will compute it for you. It wants number of successes, number of trials, confidence. So let's do an example, and we'll do it by hand, and we'll do it by calculator. See if we get the same thing, and then never do it by hand again. Okay, so how common is behavior that puts people at risk for AIDS? In the early 1990s, the landmark National AIDS Behavioral Surveys interviewed, and by the way, stop me when there's information that you might actually want to use mathematically, interviewed a random sample of 2,673 adult heterosexuals. What do they give me? N. So N is equal to 2,673. Okay, of these, 170 had more than one sexual partner in the year prior to the survey. Sorry? That is what? That's my X, number of successes. Well, actually, technically, I haven't gotten to the point of the survey yet. So I'm not 100% sure that's what X I'm looking for, but I read it, it is. Based on these data, what can we say about the proportion of all adult heterosexuals who had multiple partners in the year prior to the survey? In other words, I know my sample had 170 successes out of 2,673 trials. But now I'm curious about the whole world, not just my sample. So what can I say about the proportion of all adult heterosexuals with multiple partners in the year prior to the survey? And the question says, because what is missing right now to actually answer this question? The C level, the confidence level. The question specifically says, use 95% confidence. 0.95. So let's first do it on the calculator since it's so much easier, and then verify that we get the same thing by hand. So what is my X? 170. What is my N? 2,673. What is my confidence? Calculate. What does it give me? Actually, it gives me three things, one of which I already knew, but it gives me two more things. What does my calculator give me? Huh? Prop, and that's the test. One prop Z interval. One proportion Z interval. That's what I'm using on my calculator. It gives me P hat. What is my, no, and I already knew. What is my P hat? Okay, I'm going to write down 0.064, but if I actually use this in further calculations, I will use all of my decimals. And what else does it give me?
One question.
Yeah.
Is it different for the normal thing for those calculators? There's only usually one number,
What does it give you?
the 1.959.
You did one proportion Z interval. I'm gonna come there and take a look. Because that doesn't make any sense at all.
Is it the lower bound or the upper bound? It should give you the lower bound.
Okay, calculate.
Oh, did I press enter?
Huh?
It's that.
That. Has one proportion theta over here. X equals 170. N equals 2673. Yeah.
What is?
Don't hit enter. You hit enter, it goes away. So what is my confidence interval? What does it give me? Read it. What does it give me? No, 0.06 is p hat. What's my confidence interval? From where to where? It's an interval. 0.054 approximately to what? 0.073. That's my confidence interval. That's what the calculator provides in a second. That's what the calculator provides. Yes.
You got,
I rounded to 3 decimals. Yes.
no one on my calculator doesn't say any of those numbers.
I even know one proportion interval. We are not doing tests yet. Tests come later. So this is in the calculator. Let's do it by hand to see whether or not we get the same thing. First, how do I find p hat? X over n. So my p hat should be 170 over 2673. Let's go ahead and calculate that. 170 over 2673. What do I get? .064. So far, so good. Let's now calculate the margin of error. What's the formula for the margin of error again? Z star. This is 95% confidence. So what is my Z star? 1.96 times the square root. What's p at? Point what? Point what? 0.064. Indeed. Times. What's that?
1 minus 0.
Yeah, what is that?
0.06.
What? What's 1 minus that?
Oh.
0.936 over 2673. So that times that divided by that, square roots, multiplied by 1.96. Yeah. Because I calculated earlier that for a confidence of 95%, Z star is always 1.96. We did it. We don't got to do it again. Z star 95%. I mean confidence 95%. Z star 1.96. It's been done. We never have to do it again. Anytime you have 95% confidence, Z star is 1.96. Technically, in my calculator, it's 1.959963986. So when I multiply that by the rest, what do I get for my margin of error? What does the math give me? Should all be doing it. Math is not a spectator sport, huh? 0.00925. 366. Which means that my confidence interval, what's the left edge of my confidence interval? How do I calculate it from the numbers here? So the left edge specifically will be what? Minus. So I take p hat minus the margin of error. When I do that, I get 0.054. And how do I get the other one?
You add,
I do plus instead of minus, and I get 0.073. So we see that agrees with what the calculator provided. Of course, the calculator is much, much faster. Yes,
okay, so it's a shortcut, right? But it's.
well, it's much better to use a calculator. First of all, there's less room for making a trivial mistake, but it's so much faster. Yes,
And then on my calculator, you just press enter again, it gives you the Zstar.
okay.
Now, I don't know if you're supposed to do that.
I don't know. Yes.
Will you ever expect us to know how to do this by hand?
Why not?
Why, yes,
Because I taught it.
but if we can do it by the calculator.
I'm never gonna specifically say, do this by hand and not the calculator.
Okay.
But if I devise a question for which you can't use your calculator and you have to use a formula, then you gotta use a formula.
Should we do something like that?
If I devise a question, I'm not saying, I'm not thinking, I'd have to sit down and actually think. Yes. So what does this mean, by the way? Someone interpret this. What does this mean?
It's not good.
Huh?
It's not a.
No, I don't mean, I mean, in terms of, the question was, what percent of all adults, heterosexuals, have had more than one sexual partner in the last year? This is my confidence interval. I'm just asking you not to judge or to come up with a bad or good type answer. What does this mean in the context of this problem? How do I interpret this? Because on tests, especially the final, they do like to ask questions like, interpret this in the context of the problem. So what does this mean? Oh, the answer is 0.054, comma 0.073. What does that mean? Who wants to venture a guess? Yes. What does this mean? No. The problem was, we're curious, what percent of adult heterosexuals have had more than one sexual partner in the last year? We got 170 people said yes, out of this many that we asked. We constructed this as my confidence interval. What did we just make? What is this?
Somewhere between 5 to 7%.
Close, but no. You're missing one key part.
95% sure that someone has had more than one partner.
You started off great, but then you kind of detoured it to crap bill. Yes?
What they both said?
What?
95%, like confidence that heterosexual people between 5 and 7% have more than one partner.
That's the key. We are 95% confidence that the true value is somewhere between these two numbers. Okay, that's the whole point of the confidence interval. What are we looking for? We're looking for P. We're looking for the true value. I took a sample. This is what I got. I got 0.064. Does that mean that's a true value? No, that's just my sample value. But I'm 95% confident that the true value, whatever it is between these two numbers. Is it definitely between these two numbers? No. I'm 95% sure that it is. Now, is 95% enough for you to take that value and to go and do things with it? So like additional research or whatever the case may be? I mean, yeah, 95% confident, I'm pretty good. Yes.
So when you're referring to value, does that mean the number of heterosexuals who've had?
No, not the number, the proportion, the true proportion of adult heterosexuals is represented by the letter P. I do not know P. I will never know P. The best I can do is guess it by taking a sample and giving me a sample proportion.
But didn't they say it's 170?
Only of the 2,673 that I asked. What about the millions that I didn't ask? I can't conclude this is a true value, but I'm sure it's around there somewhere. Well, how much around there? With 95% confidence, that's the interval.
So
Between here and here.
So 5 to 7% of heterosexuals have had more than 2 partners.
So I'm 95% confident that the true proportion of adult heterosexuals who yada, yada, yada is between 5.4% and 7.3%. That's the best I can say.
So if you were, so this sample is representing the heterosexual in the United States, 5 to 7% of in the United States would.
I'm 95% confident.
Okay.
Okay, could the value be 4%? Yeah, it's, I'm pretty confident that it's not, but it could be. Does that make sense? And confidence intervals give a range of values for which we are somewhat confident, depending on how confident we want to be in the problem, that we caught the true value. Think of the net, that we caught it. Is there any value in here that is more likely than any other value for being the true value? Is there any value in here? We have this range of values. We're pretty sure it's in here somewhere. Well, that's a lot more likely than that. Do we have that? And the answer is no. Even though this was what I got from my actual sample, I have no reason to give preference to any number in this interval over any other. Any value between 0.054 and 0.073, in my mind, is as equally likely of being the true value. I do not give special preference to 0.064 just because it happened to be the true value of my sample. Yes,
So what decides the confidence percentage? Is it just like,
your choice. The more confident you want to be, the wider the interval. The wider the interval, the less useful your value is. So there's always a battle between how confident you want to be and how small the interval is so that you can actually use it for practical purposes. You will never in this course be required to come up with the confidence on your own. You will always be told what confidence to use for any problem. And if you're not told, 95%. 95% is the default confidence. If you are not told a specific confidence, use 95%. Yes.
So you can't find the confidence from.
You cannot find the confidence. No, the confidence is something about, is your philosophy about the problem. There's nothing in the math that dictates the confidence. Now, I can devise a problem where I give you the confidence level. I mean, I give you the interval, and I say what confidence led to this. I can do that, but in a practical find the confidence interval real life situation, you would never ever use math to find the confidence. You find it yourself. Okay, make sense?
How do you find confidence?
You choose. You choose. You say, I want the confidence to be 95%, and then you go with it. Now, suppose you're working on a problem, and first of all, are there any questions on how to construct a confidence interval for proportion? I mean, whether it's by hand or the calculator, it's really straightforward. Okay, but a little more challenging is the following question. Suppose I'm about to do a study and I'm worried that my confidence interval is going to be too wide. So I say in advance, I don't want my interval to be wider than a given amount. I give you the width of my confidence interval in advance. And I tell you as the researcher, I want you to make sure that my confidence interval is not wider than this. What's your only option? Well, assuming you have confidence specified. What is the only thing you can do to make sure that your confidence interval is not too wide? Increase n. The bigger the n, the smaller the width, right? So the only option you have to make sure that your confidence interval is not too wide is to make n large enough. So the question is, how can you, in advance of doing the sample, choose a sample size so that the width of your confidence interval is not too big? Okay, so again, question. Given a certain confidence, and a certain margin of error, how do we choose our sample size? If I tell you what the confidence is, I want 95% confidence. And I tell you what the margin of error is, I don't want it to be wider than 1. I want to make sure that we're not more than 1 away from the true value, whatever it is. How do we choose in advance of doing the survey? How do we choose n? So the answer is a little bit of math and a little bit of not math. Let's start with the math part. The margin of error is by definition what formula? What's the formula for the margin of error? I gave it to you earlier. P hat, wow, okay, so that's not even close, but good. P hat, 1 minus P hat over n. This is the formula for the margin of error in terms of Z star P hat. So if in advance I want to solve for n, or I want to choose my n, why don't I go ahead and just mathematically solve this formula for n? Rearrange this formula to get n by itself. Who can tell me how to do that? Whose math is mediocre enough? Yes.
Square both sides.
Square both sides. What do I get?
M squared.
M squared equals
Z star. And then all that good stuff.
all that good stuff. Could you be a little more specific?
P hat, parentheses 1 minus P hat, those parentheses over n.
Like this? Anyone want to correct him?
Squared
Which part?
after the parentheses.
Anyone want to correct him again? Yes?
You gotta divide the two over first.
Huh?
You gotta divide the two.
No, I can square right away. I mean, I would personally, but you can square both sides first.
The Z is squared.
Huh?
Z is squared.
Yeah, the Z star is also squared. You square this, you square this, you square that. You can't just square 2 of the 3. The m is squared, it becomes m squared. Z star is squared, it becomes Z star squared. And the square root of this is squared, which cancels the square root. So if you don't have the square on that, what's the next thing I do? In one step, I can get n by itself in one step. No, one step. Switch what?
Yeah, add with the N squared.
Yes. The bottom of one side can be switched with the top of the other. Anytime 2 fractions are equal, it is n squared over 1, 2 fractions. So the n is equal to Z star squared P hat 1 minus P hat over m squared. So the math part is done, but unfortunately we have a major problem. And I want to stress by saying there's nothing wrong with the math. The math is fine. But conceptually, we have a major problem here for using this formula to find n. What is that major problem?
So we need to find N squared.
No, I give you the margin of error, you take it, you square. What's the problem? Well, bigger, smaller, yeah. Yeah,
Couldn't PI change with any given sample?
sure,
So you use that in the question.
sure, but there's a bigger problem than that. Bigger problem than that. The whole point of this exercise is to choose the n to ensure that your margin of error is small enough, correct? You want to choose the n to ensure that your margin of error is small enough. We haven't chosen n yet, correct? So we haven't taken a sample yet. Forget about p hat changing depending on the sample. We don't even have a sample. How do you have p hat at all in there? It's even worse than p hat can change depending on the sample. You don't even have a p hat, right? So what do? We have 2 options. Option 1. Option 1. Use any previous knowledge of what P might be. We call this value P star. So in that case, N equals Z star P star 1 minus P star, sorry, Z star squared over M squared. And this is now, I think, can you still read it okay? Is it still dark enough you get to see it? Yeah? No? I'll go green. So use any previous knowledge of what P might be. So the question would say something like, someone else did a study 2 years ago, and they got a P value of 0.37. Great, use 0.37. If there's previous knowledge from someone else, somewhere in the past, of what P might be, just use that. Option 2. Option 2. If not, use one half. If there's no, in which case, so N equals Z star squared over 4 M squared. 1/2 times 1 minus 1/2 is 1/2 times 1/2, which is 1/4. 1/4 goes in the denominator. So option 1, if there's any previous knowledge out there, use it. Otherwise, use 1/2. Yes.
Sorry, how do you get 4 M squared?
What's 1/2 times 1 minus 1/2? Which is? No, don't go decimals. 1/2 times 1/2 is 1/4. 4 on the bottom. Here it is. 1/4. That's the 4. Yes.
Is 1/2 just one of the numbers you have to itself?
No, this one, well, yes, in this course. The actual derivation is like 2 lines. It's actually very straightforward for those who've had calculus. Essentially, if you look at this here, forget about Z star squared and M squared for a second. Let's say they're both 1 magically. I'm taking a picture. Hold on. Oh. You know, I know what it is now. They say every camera adds 10 pounds. I realize now I have like 9 cameras on me at once. So don't I? That must be the case. All right. Okay. So pick a value for P hat, any value. That's between 0 and 1. 0.5. What's 0.5? First of all, fractions. What's 1/2 times 1 minus 1/2? 1/4. Okay. Pick any other value other than 0.5, other than 1/2.
1.75.
Fine. What's 0.75 times 1 minus 0.75? No. What's 0.75 times 1 minus 0.75? No, it's not half.
0.1875.
Fractions. Why do people love decimals for some reason? I don't get it. Fractions are so much better. Fractions. 0.75 is 3/4. 1 minus 0.75 is 2.25 is 1/4. 3/4, 1/4, 3/16. 3/16 is less than a half, less than a fourth, right?
Yeah.
By using 0.5, by using 1/2, you make the largest possible n. So because you don't know what n is, well, what p is, we pick the value that will give us the largest possible sample so we can err on the side of caution. Choosing 1/2 gives us the largest possible n. If we have previous knowledge, then we use them. But without previous knowledge, we take the most conservative possible estimates, which is p is 1.5. And that will give you the largest possible n. Okay, so let's do an example. Here's an example. So far today, a lot of talking, but really only 2 formulas. Confidence interval formula and this. So question. Gloria Chavez and Ronald Flynn are the candidates for mayor in a large city. You are planning a sample survey to determine what percent of the voters intend to vote for Chavez. You will contact an SRS of registered voters in the city. You want to estimate the proportion P of Chavez voters with 95% confidence. What do I have? Oh, 95% confidence. What's my Z-star? 1.96. Okay. So again, you're contacting an SRS. That's one of the conditions. An SRS. You want to estimate the proportion with 95% confidence and a margin of error no greater than 0.03. How large a sample do you need? You want your margin of error to be no larger than 0.03. So what will I take as my margin of error? No. No, huh? Well, 0.03. I don't care if I get something smaller, but that's worst case scenario. Margin of error is no bigger than 0.03. So let's calculate it for 0.03. How large a sample do I need? Was I given any previous knowledge of what P might be?
No.
So I use option 2. N is 1.96 squared divided by 4 times 0.03 squared. Let's see what our calculator gives us here. What do I get? How much? N is my sample size. How can I ask 0.038 people? How many people do I have to ask? 0.038. Does that seem reasonable as a number of people that I have to ask? How much? Yes?
1,068.
Well, my calculator gives me 1,067.07 ... Hopefully you all got the same or something similar. I used for my 1.96. I didn't use 1.96. I used 1.959963986 because it's more exact. I use every decimal that I can, every situation that I can. So my calculator gave me this is my answer. Now I obviously cannot ask 1,067.07 people. So what do I round to?
1,067.
No.
68.
Why do I go up to 1,068?
That counts as a person.
Not exactly. Not exactly.
Greater than 1,067.
Yes. 1,067.07 is the cutoff. Anything bigger, no problem. My margin of error will be small. Anything smaller, my margin of error is going to be too big. So I always go up, even when I'm close to the number down, because 1,067 is not enough people. This is the minimum. 1,067 is not enough. 1,068, that's enough. Yes.
It gives me a number, but it says like e to the -4. How does it change?
E -4 means times 10 to the -4 power, which means you have to move the decimal 4 decimals to the left. But I would just change the mode so you're not in scientific notation mode like that.
How do we change it?
Show it to me afterwards. Yes,
Can you explain why it's 1,068?
because we're looking for the smallest number for which something will happen. This is what my math gave me. Anything smaller than this number is not good enough. 1,067 is smaller than this number. No good. 1,068 is bigger than this number. Good. So 1,068 or anything larger will make my margin of error smaller than 0.03. 1,067 will not. So the answer is 1,068 people will be enough to do it. Does that make sense? Yes,
I'm getting 8 point something. I don't know if I'm plugging in the math wrong.
you probably are. What's 1.96 squared? What's 1.96 squared? Divide that by 4, hit enter. Then divide by 0.03 squared, hit enter again. You do it all at once, and you don't put parentheses in where they're supposed to be, the calculator will probably give you the wrong answer, or at least not what you're hoping for.
Separate.
Huh?
You have to do it separate.
You don't have to. If you want to use parentheses, you can do it fine. But to err on the side of caution, when I do it on my calculator, I don't do the whole thing at once. I do this squared, enter, divided by 4, enter, divided by 0.03 squared, enter. I do it in 3 steps.
So then
I don't do it all at once, huh?
I get 10.67.1111.
Okay, so now 1068, you go up. Now, the last thing for this chapter. We talked at the very beginning. What happens if your number of successes and number of failures are not both greater than or equal to 10? You don't use that. We have something else instead. If n p hat and n1 minus p hat are not both greater than or equal to 10, but what is it again? I think that they both have to be. Let me make sure about this. I want to make sure my. Does the book even do it? I don't see it here. I'm pretty sure. But both are, I think it's greater than or equal to 5. I hold off on that for a second. I want to make sure I found it here. I always forget this one. All right, well. Here we go. No, but n is greater than or equal to 10. So we don't have 10 successes and 10 failures, but you have at least 10 trials. Okay, now, if you don't have at least 10 trials, you can't even use this one. So option 1, we use the other one that we did in the beginning. That's great. Option 2, we don't satisfy this condition, but n is at least greater than or equal to 10. Then we do the following. Then use the +4 confidence interval. And what is the +4 confidence interval? Well, again, like before, what do we have? We have x is equal to the number of successes, like before. We have n equal to the number of trials, like before. In the old case, we calculated p hat, correct? P hat was number of successes over number of trials. Now, we calculate this thing called p twiddle, is the word often used, p twiddle. And what we do is we take number of successes and add 2, and we take number of trials and +4. The +4 confidence interval. So we don't use p hat, which is x over n. We use p twiddle, which is x plus 2 over n plus 4. Yeah,
The final, are they gonna give us like a bunch of like P?
yeah. Well, what do we have so far? We have p, we have p hat. Now we have p twiddle. We have p star. And we're gonna have one more that I know, at least one more that I know
So they're gonna give us like.
of. No, you gotta know them.
They're not gonna give us one?
I don't know what they're gonna give you, but you gotta know these things. How many times have we used p and p hat already in this class? Just today, like 1,000 times. So understand what they are. It's called studying. It's called understanding what's going on. So we don't use p hats. We use p twiddle instead. P twiddle. And in that case, the confidence interval is as follows. So the confidence interval is p twiddle plus or minus z star square root p twiddle 1 minus p twiddle
How do you spell people?
twiddle 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 over n plus 4 p twiddle plus or minus z star square root p twiddle 1 minus p twiddle over n plus 4. Now on your calculator, so on calculator, x is equal to number of successes plus 2, n equal number of trials plus 4. In other words, on your calculator, when it asks for x and n, don't use the actual x and n, use the modified x and n, number of successes plus 2, number of trials plus 4. Then your calculator will do all the work for you and give you the correct confidence. If you want to do it by hand, just make these modifications. Otherwise, it's exactly the same. This is a +4 confidence interval. Let's do an example. An example near and dear to my heart. Cocaine users commonly snort the powder up the nose through a rolled up paper currency bill. Spain has a high rate of cocaine use. So it's not surprising that euro paper currency in Spain often contains traces of cocaine. Researchers collected 20 euro bills in each of several Spanish cities. In Madrid, 17 out of 20 contained traces of cocaine. By the way, no one stopped me so far, but I mean, everyone's so enthralled with the cocaine, I get it. So x equals 17, n equals 20. The researchers noted that we can't tell whether the bills have been used to snort cocaine or have been contaminated in currency sorting machines, because the bill could in theory have just come in contact with other bills. So even the researchers doing the survey said, take this with a grain of salt. Estimate the proportion of all euro bills in Madrid that have traces of cocaine. So we're looking to estimate P, the true value of all bills in Madrid. How many successes do we have? How many failures? 3. Are they each greater than or equal to 10? No, so we can't use the original confidence interval. Is n greater than or equal to 10? Yes, so we can use a new one. So on our calculator, what is x going to be on our calculator? 19. What is n going to be on our calculator? 24. And the problem says use 95%. So confidence equals 95%. So what's my Z star going to be? Or what's my confidence in the calculator? I don't actually need Z star, just need confidence. 0.95. So let's go to my 1 proportion Z interval, put in 19, put in 24. What is my confidence interval going to be?
What was your confidence interval?
I'm asking you, what's my confidence interval?
1.62919.
2.
And then 1.5541.
So we are 95% confident that the true value of bills that have been used for cocaine in Madrid is somewhere between 63% and 95%. Yes,
So if it doesn't give us like what confidence we should get.
the problem does give 95%, but if it does not, use 95%. If nowhere in the problem it doesn't give you the confidence, use 95%. Yes,
So the fact that there were 3 failures, right?
yeah,
We had to change both X and M.
yes. Well, we had to go to the second option. We couldn't use option number 1. To use option number 1, which is the formula from the beginning of class, 10 successes, 10 failures minimum. You don't have that, option 2. Do I have at least n trials? If I do, I can use this one. And that's it. So, questions?